10th International Physics Olympiad, year 1977, IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. Message me if interested. My email is fred1996@hotmail.com, or you can use a Skype name Eduard F 1996. Problem number 2. Dipping the frame in soap solution, the soap forms a rectangle film of length d and height h. White light falls on the film at an angle alpha, measured with respect to the normal direction. The reflected light displays a green color of wavelength lambda 0. Question A. Find out if it is possible to determine the mass of the soap film using the laboratory scales, which has a calibration accuracy of 0.1 milligram. Question B. What color does the thinnest possible soap film display being seen from the perpendicular direction? Derive the related equations. Constants are given date. Relative refractive index n equal 1.33. The wavelength of the reflected green light lambda equal 500 nanometers, alpha equal 30 degrees, b equal 0.02 meters, and h equal 0.03 meters. Density rho equal 1000 kg per cubic meter. Solution for problem number 2. Question A. Find out if it is possible to determine the mass of the soap film using the laboratory scales, which has a calibration accuracy of 0.1 milligram. Solution. In optics, a thin film is a layer of material which has thickness in the sub-nanometer or micron range. As light strikes the surface of the film, it is either transmitted or reflected at the upper surface. Light that is transmitted reaches the bottom surface and may once again be transmitted or reflected. The Fresnel equations provide a quantitative description of how much of the light will be transmitted or reflected at an interference. The light reflected from the upper and lower surfaces will interfere. The degree of constructive or destructive interference between the two light waves depends on the difference in their phase. This difference in turn depends on the optical thickness of the film layer, the refractive index of the film, and the angle of incidence of the original wave on the film. Additionally, a phase shift of 180 degrees or pi radians at the boundary may be introduced upon reflection at the boundary depending on the refractive indexes of the materials on either side of the boundary. This phase shift occurs if the refractive index of the medium the light is traveling through is less than the refractive index of the material it is striking. The pattern of light that results from this interference can appear either as light and dark bands or as colorful bands depending upon the source of the incident light. Consider light incident on a thin film and reflected by both the upper and lower boundaries. The optical path difference of the reflected light must be calculated in order to determine the condition for interference. Referring to the ray diagram above, the optical path difference between the two waves is the following. Let's count this difference. This delta equal N2 multiplied by OC plus CB minus N1 multiplied by AB. And because of phase shift on the lower boundary, we have to add lambda over 2 and get this result. Now let's count this equation using trigonometry. We have OC equals CB equal D over cosine beta, where beta is angle of refraction. AB equal OB multiplied by sine alpha, where alpha is angle of reflection. And because OB equal 2D tangent beta, we have AB equal 2D tangent beta multiplied by sine alpha. In our case, N1 equal 1 and N2 just equal N. Now we can rewrite first formula in the form of regular expression. Now we can use Snell law to exclude functions of beta, and we have sine alpha over sine beta equal N. It means that sine beta equals sine alpha over N, and cosine beta finally equal 1 over N multiplied by square root from N square minus sine 2 square. And again we can put this expression to the first formula. Now this left part of the formula equal to this one using only alpha, and after some calculations we have formula which we can use next. That will be 2D multiplied by square root from N square minus sine square alpha equal 2k plus 1 multiplied by lambda over 2. And now we can use this formula to count our conditions for interference. Every next thickness D. So first we can use light lambda equal lambda 0. That will be dk equal 2k plus 1 multiplied by lambda 0 over 4 square roots from N square minus sine square alpha equal 2k plus 1 multiplied by d0. And now we can count all thicknesses and all masses for these thin layers. That will be d0 equal lambda 0 over 4 square roots from N square minus sine square alpha, and after putting numbers we will get 1.01 multiplied by 10 power negative 7 meters. And after that we can count all masses for further layers. That will be mk equal rho bn multiplied by dk, and after all we have m0 equal 6.06 multiplied by 10 power negative 2 milligram, m1 equal 18.2 multiplied by 10 power negative 2 milligram, m3 equal 30.3 multiplied by 10 power negative 2 milligram, etc. And finally we can see that there is not enough calibration accuracy to measure all these films, even thinnest one. That was a solution for question A. And for question B, if the light falls at the angle of 30 degrees, then the film seen from the perpendicular direction cannot be colored. It would appear dark. So that was a solution for problem number 2.